Good afternoon. Welcome to the Jahns Distinguished Lecture series, and my name is Dr. Cheryl Hapke. I will be presenting the lecture in a few moments, but first, because the consulting company that I work for, Integral Consulting, is sponsoring this lecture, I had the opportunity to tell you a little bit about Integral Consulting. We are a fairly large environmental science and engineering firm, and you can see the web address down at the bottom is pretty straightforward, integral-corp.com. So if you see something in my brief overview of Integral here, you can go to that website to find more detail or to contact someone. Integral offers a broad range of services, of environmental science related services, everything from human health and toxicology, ecology, different engineering practices, a lot on oceans, ocean acoustics, ocean optics, and we also participate in a lot of providing services in litigation. We have a whole practice in data analytics to really help us to stay on the forefront of efficiently being able to analyze the data that we collect in the field and in other ways. And we also focus on product development, whether it's new innovative technologies for solving problems, or in some cases, it's coming up with state-of-the-art ways of presenting fairly complex scientific information to our clients or stakeholders in an easily digestible way. The markets we serve also are very broad, everything from industry and commercial services. Again, as mentioned before, a lot of litigation services, interact with trade groups. Probably one of the biggest markets that we are involved in is government, and that is all types of government. So that's government ranging from federal entities like DOD and DOE to local communities and municipalities. So these are generally overall the markets that we interact in. Our offices where we're located is all over the country, and including one in Mexico City. We have offices in Hawaii. Our primary office, our lead office is in Seattle, Washington. You can see we have a fairly strong presence up and down the West Coast, as well as the Northeast of the US. One thing that you'll see here is that Florida, where I actually sit, is not blue, and there isn't an office showing. Well, I'm a relatively new Integral employee. I started with Integral last summer, July of 2020, and I work remotely for the Santa Cruz office. So my direct colleagues are in Santa Cruz, California. But the plan is, hopefully by the end of this calendar year, the state of Florida will be red, and there'll be a little dot in right where St. Petersburg, Florida is, because the plan is to open an Integral office in St. Petersburg in the near future. So we are located and available to provide service to clients all over the country. And so more particularly, I wanted to have a chance to talk, to zoom in a little bit, to not only go over our broad market and services, but more specifically the one that I work directly with, and that's marine science and engineering. And more specifically, the service areas in the marine science and engineering practice include sediment and contaminant transport, water quality, geophysical surveys and interpretation of geophysical surveys, a whole myriad of different types of oceanographic studies, including a lot of modeling and model development, of course, field and laboratory support, coastal studies, and that actually is my realm, as we'll see on the next slide. And finally, marine renewable energy studies, which is one of our really growing service areas in the form of providing background data and solutions for wind fields and farms. And finally, drilling down even deeper, I work directly with the coastal resilience practice. The reason I sit in St. Petersburg, Florida, is in order to build out this practice on the Gulf and East coasts of the US. We have a pretty robust coastal resilience practice already up and down the West Coast, but very, very little just starting up on the East Coast. And so some of the key services that we provide within the coastal resilience practice are coastal site characterization and assessment, coastal vulnerability and risk assessment, coastal hazard adaptation, which includes sea level rise adaptation, and then finally post-event assessment and future resilience planning. In other words, maybe post-hurricane assessments and helping, for instance, communities respond better and be more resilient in the future. We also have broad expertise in the coastal realm, working on everything from, as you'll see today, large coastal landslides to coastal cliff and bluff failures, to storm flooding on mainland coastlines, on barrier islands, and even on vegetated coasts. So we have very broad in terms of the types of geomorphic settings that we cover with our coastal resilience practice. So that's just the overview I have for Integral Consulting today. I hope you'll go on our website and check us out in a little bit more detail, and feel free, of course, to reach out to me if you'd like to learn a little bit more. And I want to thank you for your time then today. Good afternoon. I am Dr. Cheryl Hapke. I appreciate the introduction from Nick. And I just wanted to acknowledge the Association of Environmental and Engineering Geologists, as well as the Geological Society of America, for inviting me to be the Jahns Distinguished Lecturer this year. It was a little bit of an odd year in terms of the COVID disrupting me to be able to do many in-person lectures, but I hope to have the opportunity to do in-person lectures this coming fall. So I appreciate you taking the time to listen to this virtual presentation today. And with that, we're going to move on to the next slide. And my presentation today is called When Mountains Move Roads. And really, it's a story about science, and specifically applied science, applied geology, engineering, and management along the beautiful Big Sur coast of California. It's important to note that this is a collaborative study that involved the U.S. Geological Survey, for whom I was working at the time, and actually had a 22-year career with the survey before moving into consulting recently, and also the University of California, Santa Cruz, as well as the California Department of Transportation and the Monterey Bay National Marine Sanctuary. So the study area, we'll just do a little bit of background first. You can see on the left-hand side of your screen a map of the study area. You can see San Francisco is here, Monterey Bay and Santa Cruz. For those of you who aren't familiar, and I think most people are familiar with the Big Sur coast, it runs just a little south of Monterey down to about San Simeon. And the key things I want to point out on this left-hand map are that the entire coastline of the Big Sur coast falls within the boundaries of the Monterey Bay National Marine Sanctuary, and that's going to be important for really the backdrop of the story. And then several other things. What we're looking at here are the Santa Lucia Range, which are part of the coast range. They're very steep, high relief slopes that plunge pretty dramatically right down to meet the waters of the Pacific Ocean. You can also see along much of the coastline there are canyons, and the continental shelf is quite narrow. So you can imagine large Pacific waves easily can reach the base of these slopes. That is part of the story of slope destabilization in this area. And the other background piece, while we have this map up, that's a little bit hard to see, is I'm going to point my cursor along it. Hopefully the recording is picking this up, but this little ribbon running right along the coast is Big Sur Coast Highway 1. And you can see that it sits right at the very edge of this landscape. And that's really going to be the focus of this presentation today. I like this shot because it provides a really beautiful perspective. It's not the clearest. It was taken out of a bounty airplane, but you can see the mountain range themselves. Monterey Bay is in the far distant in the top of the photo. And this is a quote that I love from the explorer Cabrillo. In 1542, sailed along the California coast, and for the Big Sur coast, he described the landscape as there are mountains which seem to reach to the heavens, and the sea beats on them. And the red arrow you can see points to how tiny and minuscule the Coast Highway 1 road is relative to the scale of the landscape surrounding it. So the settings for these landslides that we're going to be focusing on, just to give you the background information, the coast ranges are geologically quite young, Miocene in age, and for the most part quite complex. A lot of the area is composed of Franciscan melange material, and they're characterized, as we've already seen, by very steep slopes and deeply incised drainages. And as I also mentioned, they are openly exposed to strong Pacific storms. Just throwing up a geologic map, since this is a geological audience, you can see that it's quite complex with a lot of faults and shear zones throughout the area, which is typical of a tectonically active coastline. What I want to try to do is get you to focus, and we'll see a little bit more of the simplified geology later on in the presentation, but to focus on just those lithologies and formations that are along the road or the coastline of interest here. And so what you can see is the pink materials are predominantly island arc deposits, more granitic materials, varying lithologies. And then we've got the Franciscan subduction complex, which outcrops along the road. And even in some cases, we've got very, very old metamorphic rocks exposed in a certain area. And the variation in rock type is also going to play a role in the story that plays out today. So I just kind of wanted to give you a little bit of an idea of the geology, and you can see the faults and thrust zones along this stretch of coast as well. This is also another picture of the Coast Range, the Santa Lucia Range. I took this picture back in July of 2000. It doesn't seem like that long ago, but as you remember, even from this past summer and summers before that, this area is very subject to drought and wildfires, and the wildfires actually this past summer were quite severe. And large wildfires are often followed by catastrophic slope failures the following winter, because the fires strip the hillsides of vegetation, which do help stabilize the slopes, and it allows for higher rates of infiltration into what are already weakened materials. And finally, kind of zooming in, we've had a regional perspective. Now I'm zooming in. This is a particular site which will come up again in my presentation today, just in terms of one of the areas as a great example of this just chronic issue of landsliding. You can see these are all Caltrans earth movers and trucks out here. This was after a slide. This was in March of 2000. You can see where they've tried to stabilize and shore up the road. Areas where they actually are, what they generally try to do is to lower the gradient of the slope above the road, and by doing that, they take that material from above the road and actually deposit it below the road, overall lessening the grade and therefore stabilizing the slope. That's been their standard technique. This again, just to give you a little bit on the ground perspective, this is in an area that we were investigating. I wouldn't actually myself be standing where these two gentlemen are standing, but my colleagues chose to go for the view, so I thought this was made for an interesting photograph, and the people there are good for scale in terms of the enormity of the issue and the landscape. Okay, and then a little bit of history, because I think it's interesting to understand a little bit about the background. So the funds were first approved to build the road through Big Sur in 1919. I believe they started construction in 1932, and the road was completed in 1937. I didn't do the conversion to modern dollars, and I kind of wish I had, but the total cost of completing road construction was in 1937 was $8 million, which is a huge sum of money back then. Now that was in 1937. This photograph is from the Caltrans archives, and this is in March 1940. So you can already see just 3 years after they originally built the highway, they were already starting to experience issues of the slopes above the road becoming destabilized and material and debris falling onto the road, blocking it and damaging it in some areas. So the problem started long ago. When I first got involved in the late 90s, early 2000s along this part of the coast, at that time, prior to 2017, so there's been more recent activity, but the largest slope failure in the history of the road occurred in 1983. So after that slide, that was the Julia Pfeiffer burn slide shown in this photograph. That was the largest earth-moving operation in Caltrans history to date. Closed Highway 1 for over a year. And what you can kind of see if you do any sort of type of engineering or slope stability activities is that what they did, and this was in 1983 and 1984 when they were repairing the road, they took large volumes of material from above the road to lower the slope, the gradient of that, therefore stabilizing that hill slope, and depositing the material below the road. And so that was how they dealt with the problem. Well, you can see even in a photograph in March of 2000, that's when this picture was taken, there is still active erosion of that loose material that is going into the water, and you see these large sediment plumes. And it's also important to note that in 1983, after when that failure occurred, it was after one of the larger El Nino seasons on the West Coast, so the 82-83 winter storm season. Winter was an El Nino winter. During El Ninos on the West Coast, this part of the coast, the central coast of California, tends to get big waves and heavy rainfall, both of which to lead to slope destabilization. I alluded before in the previous slide that up until 2017, that 83 slide had been the largest. In May 2017, 50 million cubic yards of rock and debris cascaded down onto Coast Highway 1. That was referred to as the Mud Creek slide. It was analyzed extensively by my colleagues at the Santa Cruz office of the USGS, and I got to participate in some of these activities. This also closed Highway 1 for over a year. It cost $54 million to repair. So it's no small, it's not a small effort to continue to maintain these roads. Also interesting to note with the Mud Creek slide, the previous year had been a drought year, which is not uncommon anymore out in the West. And it was also what had occurred was an atmospheric river winter of 2016-2017. If you're not familiar with that term, an atmospheric river is when just the area just gets blasted with kind of continuous bands of large rain showers that just come through day after day after day, happens multiple times throughout a winter storm season. So there might not be high waves generated, but there's incredible amounts of precipitation, which of course can lead to increases in pore pressure and thus slope destabilization. And just because it, again, it keeps happening, people may or may not have read in the news or heard on the radio or TV news that just this past February 2021, a big chunk of Coast Highway 1 was taken out, the Rat Creek slide. This occurred after an extremely heavy rainfall, and if you remember, there were really, as I mentioned before, there were pretty serious wildfires last summer in the mountains of Big Sur, as well as many areas in California. And this landslide actually occurred after a heavy rainfall event. More than 6 inches fell in less than 24-hour period, and it initiated in a burn scar area from the previous summer's wildfires. So this, unlike a lot of the slides along the Big Sur coast, and especially the ones that we're going to look at in the remainder of this talk, this was more of a mud debris flow of like the upper layers of soil and rock that were loosened from the heavy rains. This was not a deep-seated landslide. They're still working to reopen the road. I do not believe it's open yet. Okay, so the bottom line, why am I telling you all this? We've got this issue with large coastal landslides, and they are a constant hazard along the Big Sur coast. And this road is the only way in and out for people who live along this coast. Granted that there aren't high population densities along this coast, but there are towns up and down the coast where people need to get to the grocery store, to get to school, to get to the hospital, and for emergency services to be able to reach this area. So keeping this highway open and maintained is pretty critical. All right, now we're going to move into the management part of the story. That was sort of the background, the geology, the geomorphology, a little bit of the history, and so we're going to move forward to the management side of things. This is another nice photo. This is that Julia Pfeiffer Burns landslide. You can see the stabilized slope here and the big sediment plume in the water. Again, this slide was taken probably in the year 2000, but you can see the coast and the steep slopes, and now the waters are part of the Monterey Bay National Marine Sanctuary. Well, the Monterey Bay National Marine Sanctuary was established in 1992. Well, so what? What does that mean? Well, up until 1992, if you remember, I mentioned that the primary protocol for reopening the roads in this area had been to excavate the hill slope above the road to reduce the gradient, thus for stabilizing that slope, and to deposit the material below the road. And once this area became a marine sanctuary in 1992, though, it was subjected to U.S. Code of Federal Regulations. And in this U.S. code, and especially number 2.2 down here, it is prohibited and unlawful for any person to discharge or deposit from beyond the boundary of the sanctuary any material or matter that injures a sanctuary resource or quality. So there was a real quandary here. Caltrans needed to clean up the road. The way they cleaned up the road was to bulldoze material down to the lower side of the road, but a lot of that material went right into the marine sanctuary, potentially damaging or injuring resources or affecting the water quality. So there was a real tug of war in terms of what we were going to do, because the thought of hauling the mass volumes of material to some inland disposal site was just, would be prohibitively expensive and would cause a lot of damage to the road itself. So now we get to the nature of the problem that you've had the background in the introduction. We have these landslides along the steep slopes of the Big Sur coast, regularly blocking or undermining or damaging Highway 1. Caltrans is the agency that's responsible for maintaining Highway 1 and getting it open. And the quickest way to do that is to push the material down off the road into, down slope of the road. But now we've got the nearshore environment being the National Marine Sanctuary. So what's the solution? Well, this is what we were looking for. We were going to try to use science to solve this problem. And what we came up with was a suggestion that the nearshore biota within what is now the Marine Sanctuary have actually evolved with catastrophic failures and therefore sediment influx to the littoral system. So if you think about it, before that road ever went in, there were constantly landslides along in this landscape, right? So all the critters and the creatures all up and down the food chain would have evolved with occasionally needing that influx. In other words, yes, it might kill some particular individuals at the moment something happens, but it does put material that is necessary to sustain the habitats. So that was the argument. And then we made the suggestion that if we could understand a little bit better where the biggest landslides were occurring historically, therefore where historically was the most material going into the marine sanctuary anyway, therefore the nearshore biota may be expecting that, so looking at it in a historical perspective, that perhaps a agreement could be made, an amendment to the regulations that would allow Caltrans to dispose of some of that material in those areas that naturally had high rates of sediment influx. So the science questions that we were asking: what locations have the highest rate of sediment influx and what's the volume? And we also wanted to understand what controlled the spatial variation of the input of that sediment. So our approach, and keep in mind, this was back in the late 90s and early 2000s, some of the techniques that we applied were revolutionary or very state-of-the-art back then, and they're extremely common now, so kind of bear with me when you see some of what we did. But essentially what we decided to undertake was a multi-scale investigation, multi-scale meaning both temporally and spatially. So we looked at the entire Big Sur coast and did some historical some extrapolation from historical data to look at sediment influx to the littoral system for the entire coastline based on 9 study sites scattered along the coast. And then we chose 3 very specific areas that had chronic problems to examine more of a time series. So rather than just having 2 dates to compare, we were looking at a time series to better understand some of the processes and some of the driving forces that were causing the landslides to occur in these areas. So the method for the regional analysis was to create DTMs, digital terrain models, from both historical 1942 and recent 1994 aerial photography using digital stereophotogrammetry. Again, these techniques are so common now and so commonly applied. But again, back in the late 90s, we didn't have LiDAR data for this part of the world. So there's no LiDAR data, and there was no such thing as structure for motion, if you're familiar with that. So we were using kind of old school techniques and some of the first people to actually generate historical topography. And then very standard nowadays, but subtract the surfaces in GIS to identify 62 years of volume change. And then we were able to calculate the loss and determine the ultimate thing we were looking at: what is the sediment yield along the coast? As I mentioned, we did this along approximately 6 kilometer stretches. And we also, to understand, some of what was driving the variability in the sediment yield inputs along the coast, we did a lot of geologic mapping so we could spatially correlate the landslides to the geology. This is just showing you what the DTMs looked like for 1942 and 1994. Again, anyone who dabbles in structure for motion or any type of digital photogrammetry has seen this, many times before, and it's not certainly not rocket science nowadays, but back then it really was cutting edge. So I just wanted to show you that. So that was our technique and our approach for the regional analysis. And then what we also did, and that's important as I go through the rest of the story, is we took that fairly complex geologic map and we zoomed in on it. We actually got some more localized geologic maps. We did some of our own geologic mapping. And what we came up with was we broke the entire Big Sur coast down into 4 distinct, we kind of clumped them into 4 distinct lithologies. One thing that didn't come out on the regional scale geologic map is a lot of the material right along the coast is actually quaternary landslide deposits. You just couldn't see that at the scale that map provided. But then you can see clearly we have areas where the Franciscan complex is exposed, areas Selenian granites are exposed, and you can see that the Franciscan complex dominates in the southern part of the area and the more granitic rocks dominate in the northern part of the area. I also just wanted to point out, you'll see these little zones 1, 2, 3, 4, so on, all the way down to 9. Those are our 9 study sites that I'll show you some data from, and those were used then to extrapolate along the entire coastline to get a regional perspective. So one of the things we did was take a Schmidt hammer. I'm sure there's people that are familiar with what a Schmidt hammer does, but what it does is it essentially it takes the rebound from a rock and that rebound value can be has been shown to be able to be correlated to an average rock strength. And so we collected a lot of Schmidt hammer data. So we were estimating the average rock strengths along the coast in these different lithologies. So again, consistently, the granitics, which are shown in pink here, are consistently much stronger. You can see that of the Franciscan Formation, the metavolcanics and the metasedimentary units are weaker than the more granitic rocks, but certainly stronger than the serpentinites, which are the weakest rock type along this coast. And now this is showing the results from our sediment yield for those 9 sections, and it's a lot of numbers. I don't expect you to try and digest all of them, but what I've done is tried to simplify this for you. Don't really worry about the volume change or the along coast length. What we did was took those values, normalized it for the area, and we're able to calculate cubic meters per kilometer per year entering the coast. And so remember, that was 1942 to 1994, so 62 years. The letters are those study areas from 1 to 9, but they are color-coded according to whether they're granitic or sedimentary rocks of the Franciscan or the melange of the Franciscan complex. And what really jumps out, and the real point of this is what I want to show you, is you can see in this column the numbers that are predominantly granitics or sedimentary rocks of the Franciscan have much lower sediment yields than do the melange rocks. So right there, we've established something about understanding when and why these landslides are occurring. This kind of shows the same information, but in a chart rather than in a table, which sometimes can be hard to look at. So what we want to do is develop the relationship between the volumetric inputs and the geology, and then as we'll see in the next couple slides, interpolate those influx in areas where we didn't actually measure them. But again, you can clearly see here, again, we have these granitic rocks and sedimentary rocks of the Franciscan giving much lower sediment yields than the melange of the Franciscan. And these were the maps that we developed for Caltrans and the Marine Sanctuary to use. And when I say we interpolated between study sections, you can see, for instance, this is the northern area. This area is the one that's dominated by granitics. And what you see is along here, you see this, ignore this outer band, you see this thin orange band in the middle. It's color-coded based on the sediment yield. So, and then the thickness of the line also helps explain the sediment yield. So you can see that along this section, it's fairly low. And then the geology between, let's say, study sections 2 and 3, which is way down here, were quite similar. So we extrapolated and made the assumption that historically, the sediment yield along this full length of coast, and based on the geology, is likely to be lower, so more in the less than 10,000 cubic meters per kilometer per year. And then just moving on to show the variation, this is the map we generated for the central section, and now you can start to see where you're getting into a thicker line and darker reds, and finally you get down here again where that geology is getting more into the Franciscan melange. We have the highest rates of input, study area 6. And again, we made dotted lines in areas where we didn't actually have observations, but the geology was similar and the rock strength measurements were similar, so we assumed that this entire section of coast, even if we hadn't observed it in the historical data, would be expected to have similar sediment influx rates. And lastly, I'll go down to this the southern section again, where you have the weakest areas are where you have that Franciscan melange. And so what this was able to do is to give the sanctuary and Caltrans tools to start talking about if they were going to allow some material to be put into the offshore or the nearshore environment, push material from the road down onto the lower slope and eventually be eroded away into the littoral system, what areas might be the best ones to do that would cause the least disturbance to the habitats and resources of the sanctuary. So for the regional analysis, the conclusions, and then we'll move on to the time series of site-specific, the historical topographic models, we were able to show that they could be used to quantify the volumetric changes along this very remote area. We found extreme variation in the sediment yield along the Big Sur coast. We were able to show that the variation appears to be directly related to the lithology and strength, and that influx rates can be interpolated to give a regional perspective of the processes. And whoops, one slide too far, sorry about that. Okay, now moving on, we're going to take a decadal scale look at more site-specific areas. So we're going to zoom in more specifically on 3 sites. And the reason for this is to understand some of the driving forces and to understand more about the processes. So just by doing an endpoint rate going back 62 years, we knew what happened, what the landscape looked like in 1942. We knew what it looked like in 1994, but that didn't tell us anything about how it evolved between those 2 time periods. So we wanted to kind of fill in that data gap of understanding how these things were happening and why. So we saw the previous studies quantified the sediment yield and identified the geospatial and geologic controls. Now, with the site-specific analyses, we want to explore the rates and the processes. So quantify short-term decadal rates of movement, analyze how they evolve morphologically through time, and then assess the factors controlling the timing of the landslides, with the idea that if we eventually wanted to get at possibly being able to predict when these things might happen, we wanted that background science. So again, same methodology, you've already seen this picture. We created the digital terrain models from aerial photography, and you'll see our time periods here, 1976, 1986, 87. They flew at 2 different times in the year, shortly after each other, 1993 and 2001. These were fairly high resolution, and we actually surveyed in the ground control points, and the nominal point spacing of the DTMs is about 5 meters. Much higher resolution than the regional analysis, which used 1/20,000 scale aerial photography. And we examined changes over 3 time periods. And these are important, 1976 to 86. This is the time period in which the 82-83 El Nino occurred, which was one of the largest El Nino events in last century along the coastline. 86 to 93, which was a relatively benign in terms of weather events. And then 93 to 2001. Anybody remembers, in 1997-98 was also a very large El Nino winter year along the California coast. So we captured 2 El Nino time periods and a more benign This is Pitkin's curve. You saw it before. This is a little bit more of it because I've merged these two slides together. But this was one of our study areas, area of chronic erosion. It's not just, this is Pitkin's curve itself along the road, but this area right here with this slope, this is called rain rocks. This is Pitkin's curve. This is called Big Slide. This whole area is just, was chronically going. This is, that this coastline, this is south of the little town of Lucia. It's been active, at least it's documented. It's been active since 1952, a very chronic area. High sediment yields here. It's not only fault controlled, but there's rotational slides and local slips. And this is in those sheared Franciscan and Quaternary landslide deposits. So here's what it looked like in 2004 after a pretty sizable event occurred. So again, just demonstrating it's chronic here. And now we're going to look at that time series. We're going to look at the subtractions of those digital elevation models. And what you can see is in this 1976 to 86 time period, so the one that had the 83 El Nino in it, especially at Big Slide, you had a large amount of material being lost above the road, some being deposited below the road, but overall, a lot of loss, high loss rates in this area. Over in the Rain Rocks area, you can see Pitkin's curve itself wasn't terribly active, but in there was, actually large areas of slips and slides, both on the slope face and then below the road as well. So fairly active year compared to 1986. To 1993, and this was, the area around Rain Rocks was a little active, but pretty overall, pretty benign. And then you compare that to the 1993, 2001, which had 97, 98 El Nino. You can see that's when the area above Pitkin's curve just let loose. A lot of movement in Big Slide, but really chronic loss, and the deposits here are some of the material from above the road then just naturally falls below the road during the slide event. All right, then another example, gray slip. You can see this is an area of chronic erosion. This is a recently, you can see they've stabilized it here. And although they've slightly stabilized the slope above the road, you can see that it's just a chronic slides and slips in the entire landslide scar. Again, if you're familiar with the geography of this region, this is just south of the town of Gorda. It occurred, the major landslide occurred in 1999 and closed the highway for 4 months. This was an area we measured of high sediment yield. The processes were classic rotational slides, and the geology is shown there. The elevation change differences maps you can see in that first El Nino period, we had a lot of slipping and sliding and loss of material. Some material accumulated in the drainages, probably coming from the upper portion of the slide, but overall, fairly substantial loss. 1986 to 1993, not much of anything. And then in 93 to 2001, again, pretty substantial losses above the road and deposition below the road. And finally, the last one we'll look at before we start to wrap up is Hurricane Point. This is north of Big Sur, the town of Big Sur. This is an area of fairly low sediment yield, but this slide was fault controlled, rotational slide. It occurred in the metamorphic rocks of the Sur complex. If you remember, those, even though they're metamorphic, there's a lot of gneisses and they're folded and faulted. They do have some resistance, and so lower sediment yields than other sections of the coastline. And the elevation different maps are coming up fast, but again, you can see 1976 to 86, there was a fair amount of movement below the road. 86 to 93, not a whole lot, some accumulation, which could just be localized slippages beyond the resolution of us being able to pick up where they started from. And then 1993 to 2001, the second El Nino time period is when that slope above the road really went off, and they lost a lot of material both above and below the road into the waters of the sanctuary. So what we were able to do for these three areas is we came up with a very simple, arithmetic to actually calculate the total net contribution of material to the littoral system. Remember, that's what we're interested in. How much material is actually going into the water of the sanctuary So we took the, how much we lost above the road. We had to calculate how much we both lost and gained below the road. And then the difference between those two would be the amount that we assumed what was deposited right into the waters of the sanctuary. And so you can see this is total net loss. So it's the total. The color codes are those 3 different areas that I showed you. And then these are the time periods on the horizontal axis, excuse me. And you can see that earlier El Nino event had a fair amount of activity, but especially in the southern areas that are dominated by the weaker rocks. The mid time series, there was much less activity overall, and then in the the one that captured the 97, 98 El Nino, much higher rates overall in all 3 areas, but highest in the weakest rocks. And this is kind of the same data showing, again, we were looking at the loss rate. We wanted to know how much went in per year. So this is sort of the same data showing roughly the same information, just in different terms. So then overall, just getting ready to wrap up, the findings of this particular, the more decadal scale are that, we were able to identify that there's a substantial increase in the loss rates, therefore contributions of material to the littoral system during El Nino years. And so, these 2 large El Nino years had a greater impact on slope destabilization, suggesting that's when material moves. We were able to document that the movement was primarily on deep-seated landslides. It mobilizes material which then accumulates on the lower slope or at the slope base, which is subsequently loaded into the waters of this marine sanctuary. And but then, there's subsequent shallow failures in the material below the road. The one is really what results in that influx of sediment to the nearshore system. So finally, overall, the outcomes of the study in total are that the sediment yield rates vary along coast, as we saw, correlated to rock material strength. We were able to demonstrate that climatic conditions control the timing of the largest inputs. And we were able to show that using elevation difference maps enabled us to really identify more stable locations, and even more specifically, stable locations within chronic slides. And as you'll see, and which made me very happy as an applied scientist, Caltrans actually incorporated a lot of the results of our this study into the Big Sur Coast Highway 1 management plan. This is our favorite area, Pitkin's Curve, which I've talked about, you've seen over and over. That's rain rocks here, and this is Pitkin's Curve slide itself. This was the slide in 2004. You've seen this earlier with the Caltrans equipment out there getting that road and the slope stabilized. And what they did is, based on the results of the digital elevation model that we generated for the Pitkin Curve area, they were able to identify pinpoints in those historical DTMs, which allowed them to know that this area here and this area here historically had been extremely stable. And what they did was then they built a bridge across it. So now when this material slips and slides, which it's going to do, the material can just run down and run right under this section of the road, depositing naturally into the marine sanctuary, because natural processes are allowed to occur. But that got them around having to push material from the highway down off, which is illegal, supposedly prohibited in marine sanctuaries. And then an acute solution here at Rain Rocks, where rocks just kind of continuously fell off the slope. They made a tunnel, but basically the rocks bounce off the top and go right down the slope. So it was kind of cool that they actually designed, engineered the road based on the results, and that was unanticipated. We hadn't planned on that being kind of a result. As I mentioned, the results were incorporated into the Coast Highway 1 management plan. So it was a real honor to have helped solve a scientific problem, and that contributed to the management of this beautiful scenic highway. So that is my story today, and with that, I want to thank you for attending and for putting up with the virtual format. My Email address is here. Obviously, we don't have the opportunity for a question and answer period, but if there was something really compelling or something that was really bugging you that you wanted to ask, feel free to reach out to me at this email. And as well, if you have any interest in talking further about Integral and some of the services we provide, I'd of course be open to that at any time. Thank you very much for your attention, and everyone have a wonderful evening.